So, you've probably heard about solar panels. They're found on houses, streetlights, and water heaters around the world to turn light into energy. But do you know the real hero behind the solar cell? Super silicon. One silicon alone can't get the job done. Together, they form monocrystalline silicon. Each silicon covalently bonds with four others to form monocrystalline silicon, which serves as the basis for the tough 3D lattice found in solar cells and semiconductors. The silicon atoms arrange themselves in a diamond cubic structure, which is a modified version of the FCC structure. It has an atomic packing factor smaller than the more common FCC and BCC structures. This is the interatomic potential graph for monocrystalline silicon, and this is the bond length. Monocrystalline silicon is created by the Swarovski process. This process puts pure crystalline silicon in a crucible and then heats it up to the melting point. A seed crystal is then put in, rotated quickly, and pulled out of the crucible to keep it as one crystal. When the liquid silicon is running low, the rotation is slowed so the crystal tapers to a point, and then it is removed from the crucible. The crucible used in this process introduces point defects called interstitials to the silicon ingots in the form of carbon and oxygen molecules. Other elements are added to the pure silicon to change the properties in a process called doping. Boron and phosphorus are two common dopant atoms. Boron causes there to be an empty silicon bond, which causes the material to be p-type. Phosphorus adds an extra electron to the material, which greatly increases electrical conductivity. Here's a boron-doped silicon phase diagram. Monocrystalline silicon is used for semiconductors because the lack of grain boundaries make it easier for electrons to move about, which would be hindered by impurities and defects. This is the phase diagram for pure silicon, and the diamond cubic structure is located in this region. There are other phases than just these two of silicon, but they require extreme pressure and are not shown on this phase diagram. It is not metastable and cannot exist with other phases except on the equilibrium line. I hope you all now know a little more about monocrystalline silicon.